All right, well, here we go. Let's talk about acids and bases in chemistry, and sometimes we also will generically refer to this as solution chemistry. So why should we study acids and bases? Acids and bases, their properties and behaviors are important in most chemical reactions, especially those involving biological processes. So hopefully we need to understand acids and bases so that we can look at how they impact and affect aqueous solutions. And furthermore, we can look at how they involve equilibrium expressions, and we look at how acids and bases impact one another in our bodies and just chemically. On a side note on this page, obviously I apologize for the little blue Schoology headings. I think you can read it anyway, but it just kind of, during the transfer from Google Gmail to here, that's what happened. Alright, so some properties of acids. The first one is that the name acid comes from the Latin for acidus, which means sour. And it refers to the sharp odor and sour taste of many acids. So one of the things that you would see associated with acids is they have a sour taste. The big one that I think about is I think of this one right here. Produces H plus ions. So you're going to see an H at the front of them. We're going to call that the Arrhenius definition in a minute. Again, they taste sour. They are corrosive. They turn blue litmus paper red. They lose their acidity when they're combined with alkalis. What is an alkali? It's a base. So acids and bases are opposites of each other. Some examples of acids: vinegar, butyric acid. Butyric acid is the acid that is made when milk spoils. That is why over time milk will become more acidic or sour, because acid means sour in Latin. Alright, now some base properties. They produce hydroxide ions, OHs, so that's what I look for there. They're bitter and soapy and slippery. They turn red litmus paper blue, and they become less basic or alkaline when you combine them with an acid. So definition-wise, Arrhenius is a guy that came up with definitions for acids, and he's going to have one for bases. And by definition, what it is, acids are indicated by the presence of hydrogen ions in a solution. Sometimes you'll also see this written as a hydronium ion, H3O+, but when you really think about it, that's just water with an extra hydrogen in it. So we'll use H+ and H3O+ interchangeably. Bases. With bases, what you want to look for is the OH-, the presence of a hydroxide. Alright, so here we have a couple of examples of acids, Arrhenius acids and Arrhenius bases. Real quickly, a little quirk again that came with when I opened this in Gmail and transferred it over. What you're going to see here is you see this little box, right? Well, what this should read is HCl, arrow, H+ ions, Cl-, meaning it breaks apart. Again, NaOH should be an arrow there, okay? Now, here's the teachable part. So acids, what acids do is they take something that's HCl. The H in the front is the indicator that it's an acid, because when it breaks down into hydrogen ions and chlorine ions. The OH here is the base indicator for an Arrhenius base. So you end up with sodium ions and hydroxide ions in solution. Again, these boxes right here should be arrows, but who cares? So let's go through and let's talk about, okay, if they're acids and bases. So here we go. Right here, you have H2CO3. The H in the front should tell you it's an acid. The OH- at the end here should tell you it's a base. You don't see anything here, but you do see a metal, a positively charged ammonium, and a negatively charged carbonate, right? Therefore, this is called a salt. And this is just water. Please take a second, pause the film, and answer these three. Good. Hopefully you just took a moment and you found out this. KOH is a base. H3PO4 is an acid. This is a salt, water. HF, presence of EH, acid. OH- and NaOH, base, salt, water. OH-, this is barium hydroxide, base. HNO2, acid, salt, water. Okay, another example here. HCl plus NaOH makes water and NaCl. The example here of the Arrhenius acid is HCl. And the Arrhenius base is NaOH. At the bottom you see the definition of neutralization, the loss of an acid and a base upon mixing. So here what we've done is we've taken an acid and a base, we put them together, and look at that. Over here, no acids or bases because it's neutralized. Okay, so here are some strong acids. Nitric acid, hydrochloric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. Strong acid means it's going to fully break apart in water. We'll talk about that later. The big thing you need to know is that strong acids fully dissociate. For definition purposes, what I would say is on a test or a quiz like the final exam, I would put your strong acids on your card. You'll be allowed a card on the exam. And likewise, here are some strong bases. Bases also fully dissociate in water, meaning they break apart. So LaOH breaks up into lithium and hydroxide ions in water. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. All examples of strong bases. Arrhenius' definition has a few disadvantages to it. It can only be applied to reactions that occur in water because it defines acid-base in terms of that. It doesn't explain why some compounds have an oxidation number of +1 for hydrogen, and it's because of that they dissolve in water to give acidic solutions, whereas some, such as like CH4, methane gas, does not do that. Only the compound that contains the OH- ion can be classified as bases, but there are other things such as Na2CO3 that have characteristics of bases, but yet are not characterized as such by the Arrhenius definition. All right, this is probably the hardest part of the whole thing. It's called Bronsted-Lowry acid bases. The big thing here that we have to understand is that in this particular example, an acid ends up being something that's an H+ donor. Bases, likewise, are H+ acceptors. Now, the reason that this is here is because sometimes water itself can act with properties of acids or bases depending on the substances in which it's reacting with. And so, like as you see down here, you'll see examples of where you have an acid and a base making a conjugate acid, a conjugate base, or here in the second one, you've got a base, water acting as an acid to make a conjugate acid and a conjugate base. Now, the big thing about these is that they will pair up. And so we're going to do some examples in just a second. So every time a Bronsted acid acts as an H+ donor, it forms a conjugate base. So we always pair those things together. So this and this go together as what we call a conjugate pair. So by definition, we said that acids are proton or H+ donors, meaning they give them away. So you can see here where it's H3O+. Why is it plus? Because this has one more hydrogen than it did as water. Therefore, 3 hydrogens, +3. Oxygen carries a -2 charge. Therefore, it's a charged particle. It's a cation. But what happens is when it takes one of these H's and gives it away, as you can see here with H2O, right, it donates it, becoming its conjugate base. Here, H2O, 1 less hydrogen, now it's OH-, etc., all the way down. All right, well, here's where this gets a little bit more difficult. So what I have here is I have 3 reactions where I want you to place these things as pairs. So I'm going to do the first one with you. So when I look at these things, I see HCl and Cl-. This is a pair. Well, how do I know that? Because I know that HCl, the hydrogen, was lost in order to form Cl-. So in order for this to occur, HCl to become Cl-, this H has to go away or be donated. By definition, that makes that an acid. Now, over here, Cl-, what we end up with is we say, okay, in order for the opposite to be true, meaning Cl to become H2O, then the Cl-, therefore, had to be the base. Or actually, we should even more specifically call it the conjugate base. Which brings us to OH minus and H2O. That is also a pairing that would occur right here. And we have to declare these two things. Well, for OH minus to become H2O, OH minus has to gain a hydrogen. Well, proton acceptors or hydrogen acceptors by definition are bases. So here, this is the base. And then likewise, what we also end up with is the water says, okay, in order to become OH minus, I have to give away one. So therefore, when I give away or donate, I'm the conjugate acid. So you end up with acid, base, conjugate base. What I'd like to do is take a couple of minutes here and do these two. At this time, you should hit pause and do these two. All right, did you get these answers? Base, acid, conjugate base, and base, acid, conjugate base. Hopefully you did. There is another definition I don't want to spend a ton of time on. It's called the Lewis acids and bases. In this case, the acid is indicated by an electron pair acceptor, whereas the base is indicated by an electron pair donator or donor. The definition is really useful for showing inorganic processes, which is what we've been doing mostly in this class. Here you see an example of a Lewis acid and a base, where you have the base donating an electron pair to the HCl. So here you have the base, and what's happening here is the electron pair is being shifted. When this occurs, you have Cl minus, and now you have H3O plus over here. Another example here of a Lewis acid and base. And here are some more examples. Like I said, I don't want to spend too much time on Lewis acids and bases, but you see some examples where you have Cl minus acting as an acid, Br2 here acting as a base, etc., moving down. All right, back to good stuff here. Electrolytes. These include acids, bases, and salts. And the big thing is that they dissociate. Now this term right here, what does that mean? It means they're broken down into smaller molecules or ions, and they conduct electricity. It's why we call them an electrolyte. You'll sometimes hear this referred to in like commercials, like Gatorade. Gatorade is a strong, source of electrolytes. Well, let's talk more about that now. So if a substance is a strong electrolyte, what it means is it breaks apart completely and is completely soluble. What does that mean? It means it fully ionizes, or the formation of ions as a result of the chemical reaction, high temperatures, electrical discharge, or radiation. How do we use it? It becomes a good conductor of electricity. Well, your body needs electrical signals in order for your brain to communicate to your hands, your feet, in athletic competition, etc. Some examples of some strong electrolytes are here, all right, and KNO3 and FeCl2 are the two that kind of cut off down there. Weak electrolytes are not as useful to us. They only partially ionize. They make insoluble salts, and these things are pretty weak. Molecular compounds are that. Weak acids are also weak electrolytes. Some examples of these are like CO2, hydrofluoric acid, magnesium oxide, etc. And the big thing with these is that they don't fully dissociate or break down in solution. Some substances are non-electrolytes, meaning they do not conduct electricity and they do not break up into individual ions at all. Examples of these include sugar and ethanol. So here's a little chart to help us to determine if a substance is a strong, weak, or non-electrolyte. First thing you ask yourself, is it an acid? If it is, yes. Is it a strong acid? If it's yes, it's a strong electrolyte and it fully dissociates and breaks apart. If it's not, then it's weak. If it's molecular, so if it's not an acid, you ask, is it molecular? If it's yes, it's a non-electrolyte, like, sugar, like we just talked about. But if the answer is no, then it could be soluble. Remember, by definition, soluble means we could break it apart. If it's a soluble ionic compound, meaning it's made of a metal and a nonmetal, then yes, it is a strong electrolyte. But if it isn't, it is weak and does not fully dissociate. All right, here's a few examples here that you'll see of some strong versus weak electrolytes. The red ones are strong, whereas the blue ones are weak. All right, we talked about this earlier, but some common strong acids. So the big thing with these common strong acids is they dissociate 100% in solution. HCl, hydrochloric acid. HNO3, nitric acid. H2SO4, sulfuric acid. HBr, hydrobromic acid. HI, hydroiodic acid. And HClO4, which is perchloric acid. Now, what does that mean to be a strong acid and to fully dissociate? Well, here what we see is we see HCl put into water, right? And you end up making H3O, hydronium ions, and chlorine ions. So these definitions, these pictures right here show you what an H3O ion looks like and what a Cl- ion looks like. The blue behind it is the water here. And as you can see, you don't see any HCl's. You see H3O pluses, 1, 2, 3, 4 of them, and you see 4 Cl's, 1, 2, 3, 4. No intact Cl- because it fully dissociated. Okay, some common weak acids: acetic acid, hydrofluoric acid, nitric acid, and let's see, this would be sulfurous acid. So here's an example now of a weak acid in water. Okay, acetic acid, hydronium ions, and the acetate ion. And what you see is you see 3 things here. You do see some H3O pluses. That means it did break down a little bit. But you see some acetate ions too. So you see that, and you see that. But you still see at the very bottom here some intact acetic acid ions. Therefore, not fully dissociating. Therefore, not a strong acid, but a weak one. And an example of a weak base, ammonia. pH scale. So when we've talked about acid base in the past, you've seen this. From 0 to 14. 7 is neutral. The hard thing for my students to remember is that as I go in this direction, I get a stronger base. As I go in this direction, I get a stronger acid. So a lower number for acidity actually means it's stronger. Okay, pH concept. Big thing we need to remember here when we do a lot of calculations is that pH by definition is the negative log of the H plus ion concentration, meaning how acidic is it. Couple more equations that we'll use. pH plus pOH equals 14. And the pOH, and yes, there is such a thing as pOH, it's the opposite of the pH scale, is the negative log of the OH minus, or the base concentration. Again, we're going to do lots of calculations involving these things. In lab, we're going to use some indicators of acids and bases. These are pH sensitive and they change color, so it's pretty cool. They generally have their color change occurring when reactions are above or below 7. And an example of one that we're going to use is something called phenolphthalein in class. We might not use bromothymol blue or methyl red, but we are going to use phenolphthalein. When we standardize solutions, we're going to do it to 3 sig figs, and we're going to analyze those substances and look for their neutralization. What this also means is we can also standardize by knowing and determining the concentration of these solutions. And lastly, in lab, we're going to do things called titrations. This is where we're going to use that phenolphthalein. And what we can do is we can take an acid and add base to it to the point where it goes from being an acid to a base, because that neutralization point will occur eventually. The end point is when one reactant is completely reacted with the other, is indicated by a color change. We're going to talk about the difference between an end point and an equivalence point in class. Yay!